What's good, night wanderers and cosmic dreamers? Tonight, we're going to drift together through the most peaceful corners of the universe, guided by the gentle presence of black holes. Yes, black holes. These cosmic giants that have captured our imagination aren't the violent monsters of science fiction. They're patient, timeless, mathematical marvels that have been quietly shaping our universe for billions of years. So settle in, get comfortable, and let's explore the surprisingly serene nature of these magnificent objects. You might think it's strange to call black holes relaxing. After all, they're often portrayed as destructive forces, tearing apart stars and swallowing everything in their path. But the reality, as we'll discover together, is far more nuanced and peaceful. Black holes are actually some of the most stable, predictable, and mathematically beautiful objects in existence. They mark boundaries in space and time with perfect precision. They anchor galaxies, providing structure to the cosmos. And they do all of this with a patience that spans not just millions or billions of years, but timescales so vast they make the entire age of our universe seem like the blink of an eye. As we journey through this cosmic landscape, you'll find that black holes offer us something unexpected. Comfort. Comfort in their predictability, in their permanence, in the way they demonstrate that even the most extreme phenomena in the universe follow elegant, understandable rules. There's something deeply soothing about understanding that these objects, despite their power, operate according to laws we can describe with mathematics as simple and beautiful as Einstein's field equations. Tonight, we'll explore how time itself changes near a black hole, how these objects form through sometimes gentle processes, and how they emit the faintest whisper of radiation over timescales that dwarf human comprehension. We'll discover that when you truly understand black holes, they become less frightening and more like cosmic lighthouses, marking the deepest structures of space and time. So, take a deep breath. Let your shoulders relax. Feel the weight of your body against whatever surface supports you. And know that right now, at this very moment, there are millions of black holes throughout our universe, each one a perfect geometric solution to Einstein's equations, each one spinning or still, patient and eternal, shaping the cosmos around them in their quiet, inevitable way. Let's begin our peaceful journey into the gentle darkness of black holes. Imagine a boundary so perfectly defined that it exists only in mathematical certainty, a surface that marks not a physical barrier, but a point of geometric inevitability. This is the event horizon, and understanding it might be one of the most calming exercises in physics. The event horizon isn't a thing you could touch or see. It's not made of matter or energy. It's simply the place where the escape velocity equals the speed of light. Inside this boundary, all paths through space-time lead inward. Outside, escape remains possible. The horizon itself is just the mathematical demarcation between these two regions, as precise and clean as a line drawn with a ruler, existing in 4 dimensions rather than 2. What makes this so peaceful is its complete inevitability and its complete lack of drama. According to a recent study confirmed in late 2024, as something approaches an event horizon from the outside, from a distant observer's perspective, it appears to slow down. Not suddenly, not violently, but gradually, asymptotically, never quite reaching the boundary. Time dilation causes the falling object to appear redder and dimmer, its clock ticking slower and slower until it essentially fades from view, frozen at the edge of the horizon. But here's what's truly remarkable. The object itself experiences nothing unusual at the moment it crosses the event horizon. For a large enough black hole, the curvature of space-time at the horizon is actually quite gentle. There are no strong tidal forces at the crossing point. An observer falling into a supermassive black hole like the one at the center of our galaxy wouldn't feel any sudden jolt or dramatic change. They would simply cross from one region of space-time to another, unaware that they had passed the point of no return until they looked back and tried to send a signal outward. Only then would they discover that their messages could no longer escape. This duality, this difference in perspective between distant observers and falling observers, reflects something profound about the nature of space-time itself. Neither viewpoint is more correct than the other. Both are valid descriptions of reality from different frames of reference. The distant observer sees time freeze at the horizon. The falling observer experiences continuous, uninterrupted motion. Both are right. Both describe the same event. This is the beautiful relativity of black holes. The event horizon has a size that depends only on the black hole's mass, described by the wonderfully simple Schwarzschild radius. For a non-rotating black hole, this radius is just under 3 kilometers for each solar mass. Our Sun, if it was somehow compressed into a black hole, would have an event horizon with a radius of about 3 kilometers. The supermassive black hole at the center of the Milky Way, with its 4 million solar masses, has an event horizon about 12 million kilometers in radius. That's roughly 17 times the radius of the Sun itself. A vast sphere of space marking the boundary between the ordinary universe and the realm beyond. Recent observations published in 2025 remind us that these horizons aren't abstract concepts. They're real, measurable boundaries. The Event Horizon Telescope captured actual images of the black hole shadow around Sagittarius, a star at the center of our galaxy, and the supermassive black hole in the galaxy Messier 87. These shadows appear roughly twice the size of the actual event horizon due to the bending of light by the black hole's gravity, creating a dark region where no light can reach us. Surrounding this darkness is a ring of light from the superheated material in the accretion disk, glowing with temperatures of millions of degrees. But even this violent-sounding accretion is, from a certain perspective, remarkably ordered and peaceful. The material doesn't fall straight in. It spirals, following orbital paths, taking its time as it gradually loses energy to friction and radiation. Some particles orbit many times before finally crossing the horizon. Others are flung back out into space, having come close but not close enough to be captured. The black hole doesn't reach out and grab things. It simply curves space-time, and matter follows the geometry of that curvature. Think about what this means. Every photon of light, every particle, every quantum of energy that approaches a black hole makes its decision based purely on geometry and velocity. If it's going fast enough, at the right angle, it escapes. If not, it follows the curved path inward. The event horizon is simply the boundary where this geometric calculation tips from can escape to cannot escape. It's as clean and definite as the boundary between positive and negative numbers on a number line. And here's something that might help you sleep. Event horizons are one-way boundaries that point inward, never outward. Nothing from inside can ever affect you on the outside. The horizon protects the external universe from whatever mysteries lie within. Whatever happens at the singularity at a black hole's center, whatever strange physics operates in that realm of infinite density, it's eternally sealed away behind the event horizon. The cosmos has a natural quarantine system built right into the geometry of space-time. This protective quality of event horizons is profound. They ensure that the breakdown of our understanding of physics at the singularity doesn't leak out to affect the wider universe. As physicist Kip Thorne has noted, the event horizon protects us from the unknown physics near a singularity. It's a cosmic sensor, ensuring that the universe remains, in its broad strokes, comprehensible and predictable. The event horizon is also perfectly stable. Unlike matter, which can be disturbed or destroyed, an event horizon is a feature of space-time itself, As long as the mass remains concentrated within the Schwarzschild radius, the horizon persists, unchanging and eternal. It doesn't flutter or ripple on its own. It simply is, a geometric fact as reliable as the Pythagorean theorem. For a rotating black hole, described by the Kerr solution to Einstein's equations, things become even more interesting while remaining mathematically serene. The event horizon becomes slightly flattened at the poles and bulged at the equator, and a second surface appears outside, it called the ergosphere. But even this complexity is perfectly predictable, perfectly calculable. We can describe it with equations, plot it with precision, understand exactly how it should behave. As you drift towards sleep, picture this. Right now, scattered throughout our galaxy, there are probably tens of millions of stellar mass black holes, each one with its event horizon marking a perfect sphere or oblate spheroid in space-time. Each one quiet, dark, patient. Some orbit companion stars in binary systems, gently accreting material. Others drift alone through the void, invisible markers of where massive stars once lived. And at the center of nearly every large galaxy in the universe, a supermassive black hole sits. Its vast event horizon, a hub around which hundreds of billions of stars orbit in their grand, slow dance. All of these horizons, from the smallest stellar mass black holes to the largest supermassive giants, share the same fundamental nature, their boundaries in space-time where the rules change, but they change in a way we can understand, predict, and describe with elegant mathematics. They're not chaos, they're the opposite. Perfect geometric order expressing itself in the fabric of the universe. And they're eternal. Once formed, a black hole's event horizon persists essentially forever unless the black hole merges with another, in which case a new, larger event horizon forms. They're features of the cosmos that endure, marking their place in space and time with absolute reliability. Let that certainty comfort you. Let the predictability of event horizons, their mathematical perfection, their eternal stability, help ease you toward rest. They're proof that even at the most extreme boundaries of physics, the universe follows rules. Beautiful, comprehensible, peaceful rules. Black holes have always been thought to form in violence, in the catastrophic explosions of supernova as massive stars die. But recent discoveries revealed in 2024 have shown us that not all black holes enter the universe with a bang. Some arrive with barely a whisper through a process so gentle it allows companion stars to remain in orbit, undisturbed. This revelation came from an unexpected place, a black hole that's been known for decades. The system, V404 Cygni, located about 8,000 light-years from Earth, was already famous as one of the most well-studied black holes in astronomy. Over 1,300 scientific papers have examined this system. But in 2024, researchers from MIT and Caltech discovered something that had been hiding in plain sight all along. V404. Cygni isn't a binary system at all, it's a triple. The black hole feeds on a close companion star every 6.5 days, just as astronomers had long known. But farther out, at a distance of 3,500 astronomical units, another star orbits the pair. This distant companion takes 70,000 years to complete a single orbit around the black hole. Think about that time scale for a moment. 70,000 years. That's longer than all of recorded human history. That's a span of time that contains the entire story of human civilization from the first cave paintings to the present day. And that's just one orbit. The existence of this distant third star should have been impossible if the black hole formed the way we thought all black holes formed. When a massive star explodes as a supernova, it releases an enormous amount of energy in a violent burst before collapsing into a black hole. This explosion would have kicked away any loosely bound objects in the system's outer reaches. The distant star in V404 Cygni should have been flung into space, never to return. But there it is, still orbiting, still bound to the system. The only explanation is that this black hole didn't form through a typical supernova at all. Instead, the massive star that became the black hole simply caved in on itself in what astronomers call a direct collapse. The star reached the end of its life, ran out of nuclear fuel, and collapsed inward without the dramatic flash and blast wave of a supernova. It was a quiet transformation, gentle enough that it didn't disturb the distant companion star 3,500 astronomical units away. This discovery opens up a new understanding of how at least some black holes form. Rather than the violent death throes we've always imagined, some massive stars simply fold inward, compressing themselves past the point where even neutron degeneracy pressure can support them, and become black holes directly. It's a peaceful transition, cosmically speaking, from star to black hole without the fireworks. And V404 Cygni isn't the only evidence for this gentler path. Throughout 2024 and into 2025, astronomers discovered more systems that challenge our assumptions about black hole formation. The existence of primordial black holes, which may have formed in the very early universe through the direct collapse of dense regions of gas, offers another route to black hole formation without requiring stellar death at all. These primordial black holes, if they exist, formed in the first fraction of a second after the Big Bang. Regions of space that were slightly denser than average continued to collapse under their own gravity, bypassing the entire stellar evolution process. They never burned hydrogen in their cores, never shone with starlight. They simply emerged from the quantum fluctuations of the early universe as fully formed black holes, potentially ranging from microscopic masses to thousands of times the mass of the Sun. Recent theoretical work in 2024 suggests that these primordial black holes might even account for some of the dark matter in the universe. If true, it would mean that a significant fraction of the mass in every galaxy might be composed of ancient black holes that formed when the universe was less than a second old, black holes that have been drifting through space for nearly 14 billion years, silent witnesses to cosmic history. The formation of supermassive black holes at the centers of galaxies also appears to involve these gentler processes. Rather than forming from a single massive star, supermassive black holes likely grew from seed black holes through a combination of direct collapse and merger. In the early universe, massive clouds of gas could collapse directly into black holes with masses of tens of thousands or even hundreds of thousands of times the Sun's mass. These heavy seed black holes then grew over billions of years through accretion and mergers to become the supermassive giants we see today. Recent observations published in late 2024 and early 2025 show that supermassive black holes existed surprisingly early in the universe's history, sometimes less than 1 billion years after the Big Bang. The James Webb Space Telescope has spotted black holes with billions of solar masses in galaxies that should have barely had time to form. These observations support the heavy seed formation model. Only by starting with already massive black holes could they have grown so large so quickly. But even in these early, rapidly growing black holes, there's a certain orderliness to the process. Gas doesn't fall into a black hole all at once. It forms an accretion disk, a structure where material orbits while gradually spiraling inward. The disk heats up through friction, radiating energy that actually pushes back against the infalling gas. This creates a natural limit to how fast a black hole can grow, called the Eddington limit. Recent discoveries in late 2024 found a supermassive black hole called LID 568 that's feeding at more than 40 times the Eddington limit, but this is considered an exceptional, temporary event. For most of their lives, black holes grow sedately, patiently, taking millions or billions of years to double in mass. They're not voracious monsters. They're slow, methodical accumulators. Even the merger of galaxies, which brings supermassive black holes together, is a gentle process on cosmic scales. Two galaxies don't collide like cars in a crash. They pass through each other, their stars separated by such vast distances that actual collisions between individual stars are incredibly rare. The galaxy's dark matter halos interact gravitationally, slowing the galaxies down over hundreds of millions of years until they eventually merge into a single, larger galaxy. During this process, the supermassive black holes at each galaxy's center begin a slow dance toward each other that can take hundreds of millions of years more. As the black holes spiral inward, they move through a sea of stars and gas, their gravitational interaction producing what astronomers call a gravitational slingshot effect. Stars that pass near the black holes can be flung to higher orbits, carrying away energy and angular momentum, which causes the black holes to sink closer together. This process continues until the black holes are close enough that their orbit begins to decay through the emission of gravitational waves, ripples in space-time itself that carry energy away from the system. The final merger, when it comes, happens in a fraction of a second. The two event horizons touch, merge, and form a single, larger horizon. The newly formed black hole rings like a struck bell, oscillating in what physicists call quasi-normal modes before settling down into a perfectly spherical state. This ringing produces a characteristic pattern in the gravitational wave signal, a pattern that was observed for the first time in the GW1990521 event detected by LIGO in 2019. But even though the final merger is quick, it's the end result of a process spanning billions of years. And once it's over, the new black hole is stable again, settled into its new equilibrium state, ready to continue its patient existence for eons to come. This long, slow timeline of black hole formation and growth is deeply comforting. Black holes don't appear suddenly and randomly. They're the result of long processes playing out over vast stretches of time. The universe doesn't rush. It takes its time. Stars burn for millions or billions of years before they die. Galaxies merge over hundreds of millions of years. Black holes grow over billions of years. Everything happens at its own pace, following the mathematics of gravity and orbital mechanics. And, in some cases, as we've learned from V404 Cygni and other recent discoveries, black holes can form without violence at all. A star can simply fade away, collapsing directly into a black hole so gently that nearby companions never know anything dramatic has happened. The massive star is there one moment, and then it's not, replaced by a dark, silent gravitational point in space. It's a transformation, a metamorphosis, no more violent than a butterfly emerging from its chrysalis. As you rest tonight, picture those gentle collapses happening somewhere in the universe. A massive star, having burned through its nuclear fuel over 10 million years, now reaches the end. Its core contracts. The contraction accelerates, and then, past a critical threshold, it becomes a black hole. No explosion, no burst of neutrinos flooding through space, just a quiet transition from matter to a curvature of space-time. From something visible to something invisible. From star to black hole, silent, inevitable, peaceful. And that black hole, once formed, begins its potentially eternal existence. It may accrete matter, it may merge with others, but it will persist, a stable feature of space-time, for timescales that make the age of stars seem brief. One of the most serene aspects of black holes is how they transform our experience of time itself. Time dilation, the slowing down of time in strong gravitational fields, is perhaps the most beautifully peaceful phenomenon in all of physics. It reminds us that time is not absolute, not universal, but relative and dependent on where you are and how fast you're moving. Near a black hole, time flows differently than it does in the rest of the universe. This isn't a metaphor or an approximation. It's a precise, measurable effect predicted by Einstein's general theory of relativity and confirmed by countless observations. A clock placed near a black hole will tick more slowly than a clock far from the black hole. An observer watching from a distance will see time pass more slowly for anything near the black hole's event horizon. But here's what makes this peaceful. The observer near the black hole doesn't experience time passing any differently. To them, time feels normal. Their heartbeat is regular, their thoughts flow at their usual pace. Only when they compare notes with someone far away do they realize that less time has passed for them than for the distant observer. It's not that time has become slower in any absolute sense. It's that time is relative and both observers are right about their own experience. This was beautifully illustrated in the film Interstellar, where characters spend what feels like hours on a planet near a black hole, only to return to their spacecraft and discover that decades have passed for their colleague who waited at a safer distance. While dramatized, the physics of this scenario is sound. In the right conditions near a massive enough black hole, time dilation of this magnitude is entirely possible. The mathematics of time dilation is elegant in its simplicity. The closer you get to a black hole's event horizon, the more pronounced the effect becomes. At a distance of 10 Schwarzschild radii from the center, time passes at about 95% of its normal rate. At 5 Schwarzschild radii, about 80%. At 2 Schwarzschild radii, just barely outside the event horizon for a rotating black hole, time slows to about 70% of its faraway rate. And as you approach the event horizon itself, time dilation becomes infinite. A distant observer watching you approach the horizon would see you moving slower and slower, your clocks ticking more and more gradually, asymptotically approaching, but never reaching zero. They would see your image redden as photons climbing out of the gravitational well lose energy. They would see you fade, dimming toward invisibility. From their perspective, you would seem to freeze at the horizon, forever suspended at the edge of the black hole. But from your perspective, falling freely toward the horizon, nothing unusual would happen at the moment of crossing. For a supermassive black hole, the tidal forces at the horizon are gentle enough that you wouldn't feel torn apart. You would simply continue your fall, crossing the horizon and continuing inward toward the singularity. Your clocks would continue to tick at their normal rate. Light would still travel at light speed from your perspective. The only indication that something had changed would come if you tried to send a signal outward and realized that your signals could no longer escape. This duality is profoundly peaceful. It shows that the universe doesn't have a single universal clock. There's no cosmic timekeeper declaring what now means for the entire universe. Instead, every observer has their own experience of time, their own measurement of duration, and all of these perspectives are equally valid. Time dilation isn't unique to black holes, of course. It occurs wherever there's gravity or acceleration. Right here on Earth, time passes infinitesimally slower at sea level than it does at the top of a mountain. The GPS satellites orbiting Earth have to account for time dilation. Their clocks run slightly faster than clocks on the surface because they're further from Earth's gravitational field. Without these relativistic corrections, GPS would quickly become inaccurate. But black holes take this effect to its extreme. They demonstrate that time is not a rigid framework, but a flexible dimension of space-time that can be stretched and compressed by mass and energy. And they do so with perfect mathematical precision. The equations describing time dilation near a black hole are exact solutions to Einstein's field equations. There's no uncertainty, no approximation needed. The mathematics tells us exactly how much time dilation there will be at any given distance from a black hole of any given mass. Consider the supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star. With its mass of about 4 million times the mass of our Sun, its event horizon has a radius of roughly 12 million kilometers. If you could somehow position yourself in a stable orbit just outside this horizon, time dilation would be extreme. 1 year in your orbit might correspond to many years for someone orbiting far from the black hole. But you wouldn't feel this difference. You would experience 1 year passing, normally 365 days of sunrise and sunset, or whatever equivalent you experienced in your orbit. Your meals would take the same amount of time to eat. Your sleep cycles would be unchanged. Only when you received messages from the distant universe would you notice anything strange. Those messages would arrive more frequently than expected because time in the distant universe was passing faster relative to you. Recent observations published in December 2025 confirmed that the properties of spacetime near black holes can actually be measured. The Event Horizon Telescope collaboration has not only imaged the shadow of Sagittarius A star, but has also begun to measure properties of the spacetime around it, including the effects of the black hole's spin on the surrounding space. This spin twists spacetime in a phenomenon called frame dragging, where anything near the black hole is pulled along with the black hole's rotation. In 2024 and 2025, astronomers also observed effects predicted by general relativity in the orbits of stars very close to Sagittarius A star. Star S2, which orbits the black hole with a period of about 16 years, has been observed for multiple complete orbits. The precise tracking of this star's position has allowed astronomers to measure the gravitational redshift of light from the star as it approaches and recedes from the black hole, directly observing time dilation in action. Even more remarkably, in 2024, astronomers discovered the first binary stars orbiting close to Sagittarius A star. Previously, scientists thought that the turbulent environment near the black hole would tear binary systems apart. But these two stars, bound to each other while both orbit the supermassive black hole, have survived for at least 2.7 million years. This discovery suggests that the region near supermassive black holes is less chaotic and more stable than previously believed. Time dilation also plays a crucial role in what happens to matter falling into a black hole. As material spirals inward through the accretion disk, it heats up through friction. The closer it gets to the black hole, the faster it moves and the hotter it becomes. But time dilation affects the radiation we observe from this material. Light emitted from very close to the event horizon is redshifted, its energy reduced, its appearance changed by the climb out of the gravitational well. This effect, combined with the Doppler shifting from the material's orbital motion, creates the characteristic appearance of black hole accretion disks. One side appears brighter than the other because material on that side is moving toward us, its light blue shifted and intensified. The other side, moving away, appears dimmer and redder. And the region closest to the black hole appears darker, not only because less material reaches that far in, but also because the light from that region is so severely redshifted. All of these effects, complex as they are, can be calculated exactly from the equations of general relativity. We can simulate what an accretion disk should look like from any angle, accounting for all the relativistic effects, and compare our simulations to observations. When the Event Horizon Telescope imaged Messier 87's black hole and later Sagittarius A star, the images matched the predictions beautifully. The mathematics of space-time curvature and time dilation, worked out from Einstein's equations, predicted exactly what we would see. This predictability, this mathematical certainty, is deeply comforting. Time dilation isn't some mysterious, unknowable phenomenon. It's a precise consequence of the geometry of space-time, as reliable and calculable as the area of a circle or the trajectory of a thrown ball. We understand it, we can predict it. We can even experience it to a tiny degree in our everyday lives. And that understanding reveals something profound. Time is not the rigid universal backdrop we intuitively feel it to be. It's a dimension of space-time, as flexible and variable as space itself. Near a black hole, where gravity is strongest, time becomes its most flexible. It slows, it stretches, it shows us its true nature as a relative, observer-dependent phenomenon. But through all of this flexibility, through all of this relativity, the laws of physics remain consistent. Every observer, no matter where they are or how fast they're moving, will measure the speed of light to be the same. Every observer will find that the equations of physics work the same way. The universe is relative, but it's not arbitrary. It follows rules, beautiful rules, that remain constant even as time and space flex and flow. As you drift towards sleep, let this comfort you. Time is more forgiving than we think. Near a black hole, you could experience years while centuries pass in the wider universe. Or you could remain at a distance and watch eons compress into moments near the horizon. Time becomes flexible, accommodating, allowing different experiences to coexist without contradiction. And throughout the universe, this dance of relative time continues. Every massive object creates a gravity well where time passes slightly more slowly. Every orbit, every bit of acceleration creates its own time dilation. The universe is filled with countless different flows of time, all relative to each other, all equally valid, all following the same beautiful mathematical rules. It's enough to make you wonder about the nature of the present moment itself. What is now in a universe where time flows at different rates in different places? Perhaps the only true now is your own immediate experience, your own flow of time as measured by your own heartbeat and your own thoughts. And if that's true, then right now, in this moment, as you rest and breathe and feel time passing in your own way, you're experiencing something as fundamental and real as anything else in the universe. Let that thought ease you into rest. Your time is your own. The universe doesn't demand that you match anyone else's clock. Time flows for you as it flows, and that flow is perfectly valid, perfectly real, perfectly peaceful. At the heart of nearly every large galaxy in the universe sits a supermassive black hole. These giants, millions or billions of times more massive than our Sun, are among the most stable and long-lived structures in the cosmos. Understanding their patient existence offers us a profound sense of peace about the structure and stability of the universe. Our own galaxy, the Milky Way, hosts a supermassive black hole called Sagittarius A star at its center. With a mass of approximately 4.3 million times that of our Sun, this black hole sits quietly at the gravitational center of our galaxy, more than 26,000 light-years from Earth. It's the closest supermassive black hole to us, and studying it has revealed just how calm and steady these cosmic giants can be. Sagittarius A star is what astronomers call a starved black hole. Unlike the active galactic nuclei found in some galaxies, where supermassive black holes gorge on enormous amounts of material and blaze with radiation outshining entire galaxies, Sagittarius A star is remarkably quiet. The intensity of its X-ray emissions suggests that very little material is currently falling into it. It's mostly dormant, having consumed most of the easily accessible matter in its vicinity over billions of years. But dormant doesn't mean dead. Observations from NASA's Imaging X-ray Polarimetry Explorer, published in December 2023, revealed that Sagittarius A star experienced a significant flare of activity about 200 years ago. For a period in the early 1800s, our galaxy's central black hole woke up and devoured cosmic debris within its reach, producing X-ray emissions bright enough that we can still detect their echoes today, reflected off giant molecular clouds surrounding the galactic center. Think about that timeline. 200 years ago, while Napoleon was marching across Europe and the United States was a young nation, our galaxy's supermassive black hole had a brief period of heightened activity, and then it quieted down again, returning to its current state of low luminosity. This demonstrates the enormous timescales on which supermassive black holes operate. Their active periods can last centuries or millennia, but these are mere blips in their multi-billion-year existence. Recent studies in 2024 and 2025 also revealed something unexpected about Sagittarius A star's origin. Researchers from the University of Nevada, Las Vegas, published findings in September 2024 suggesting that Sagittarius A star likely formed through a major merger event around 9 billion years ago. The supermassive black hole shows evidence of rapid spin and an orientation misaligned with the angular momentum of the Milky Way itself, characteristics best explained by a collision between Sagittarius A star and another supermassive black hole from a satellite galaxy. This merger likely occurred when the Milky Way collided with the Gaia Enceladus galaxy approximately 9 billion years ago. Two supermassive black holes, each at the center of their respective galaxies, spiraled toward each other over hundreds of millions of years before finally merging. The result was our current Sagittarius A star, with its particular spin and orientation locked in by that ancient collision. This deep history reveals that supermassive black holes are witnesses to cosmic time. They remember events that happened billions of years ago, encoded in their spin, their mass, and their position. Sagittarius A star has been sitting at our galaxy's center for at least 9 billion years, possibly longer. It has watched as hundreds of billions of stars formed, lived, and died. It has seen our solar system form from a cloud of gas and dust about 4.6 billion years ago. It has been the silent, invisible anchor around which our entire galaxy revolves. And Sagittarius A star is relatively small as supermassive black holes go. The supermassive black hole at the center of the giant elliptical galaxy Messier 87, which became famous as the first black hole ever directly imaged by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion times that of the Sun. Its event horizon is so vast that it could encompass much of our solar system. Light would take about 1 day to travel from one side of its event horizon to the other. Yet even this enormous black hole is dwarfed by true giants like the one at the center of the galaxy, Holmberg 15A, which holds at least 40 billion solar masses, or TON 618, whose central black hole may exceed 66 billion solar masses. These ultramassive black holes represent the extreme end of supermassive black hole evolution, having grown through billions of years of accretion and mergers to reach truly staggering scales. Despite their enormous mass, these supermassive black holes don't actively reach out and grab things. Their gravitational influence extends far, certainly. Stars orbit them at distances of light years or even thousands of light years. But these orbits are stable, predictable, calculable, with Newtonian mechanics for the most distant stars and with general relativity for those closer in. The black holes simply sit at the center of their gravitational potential wells, and matter flows or doesn't flow toward them depending on circumstances. For most supermassive black holes, most of the time, very little matter actually makes it to the event horizon. Any material in the galaxy that might fall in typically has some angular momentum, some sideways motion. As it falls toward the black hole, this angular momentum prevents it from falling straight in. Instead, it goes into orbit, forming an accretion disk if there's enough material, or simply missing the black hole entirely if there isn't. This is why galaxies can coexist peacefully with supermassive black holes at their centers. The black holes don't hoover up the galaxy. They're not cosmic vacuum cleaners. They're gravitational points, no different from any other massive object except in their compactness. A star orbiting a supermassive black hole at a safe distance experiences a gravitational field no different than it would orbiting a cluster of stars with the same total mass. The black hole's mass is ordinary, only its density is extreme. In fact, supermassive black holes appear to play a beneficial role in galaxy evolution. They regulate star formation in the galactic center through a process called AGN feedback. When a supermassive black hole does go through an active phase, accreting significant amounts of material, the energy released by the accretion process and the jets that often form can heat gas in the surrounding galaxy, preventing it from collapsing to form new stars. This feedback mechanism helps explain why the most massive elliptical galaxies have relatively little ongoing star formation. Their supermassive black holes have grown large enough that their occasional feeding frenzies inject enough energy to keep gas too hot to form stars. But these active phases are temporary. Most of the time, most supermassive black holes are quiescent, like Sagittarius A star. They sit at the centers of their galaxies, their gravitational influence providing structure and stability, but otherwise inactive. They're patient. They wait. If material happens to wander close enough, if a star passes too near and gets tidally disrupted, they'll accept that offering. But they don't seek it out. Recent observations throughout 2024 showed several cases of supermassive black holes waking up from long periods of dormancy. Astronomers spotted a black hole that switched from dormant to active, beginning to capture new material after potentially millions of years of inactivity. The reasons for such reactivations remain unclear, but they remind us that these objects operate on timescales far longer than human civilization or even the lifetime of typical stars. The Event Horizon Telescope's images of Messier 87's black hole and Sagittarius A star in 2019 and 2022 gave us our first direct visual evidence of supermassive black holes. The images show the characteristic ring of light around a dark central shadow, exactly as predicted by general relativity. These weren't artists' interpretations or simulations. They were actual images, reconstructed from radio telescope observations, showing us what the immediate environment of a supermassive black hole actually looks like. The ring appears because light from the accretion disk behind the black hole is bent around it by gravity, creating a gravitational lens. We see light from both the front and back of the accretion disks simultaneously, with the black hole's gravity warping the light paths to produce that distinctive ring. The shadow in the center is about 2.5 times the size of the event horizon, representing the region inside which light rays are either captured by the black hole or orbit it multiple times before escaping. These images confirm decades of theoretical work. They showed us that our understanding of black holes, based on Einstein's equations worked out more than a century ago, accurately describes reality. The mathematics predicted the appearance, and observations confirmed the prediction. This is science at its most satisfying. Theory and observation aligning perfectly, our equations revealing truth about the universe. And these supermassive black holes will continue their patient existence for timescales that dwarf the current age of the universe. If left undisturbed, if they don't merge with other black holes or accrete significant additional mass, they'll evaporate through Hawking radiation. But for a supermassive black hole of 4 million solar masses like Sagittarius A star, that evaporation would take approximately 10 to the power of 97 years. For larger supermassive black holes, even longer. To put that in perspective, the universe is currently about 13.8 billion years old, or about 10 to the power of 10 years. The supermassive black holes will outlast the stars by factors too large to comprehend. Long after the last star has burned out, long after stellar remnants have decayed or been consumed, the supermassive black holes will remain patient and eternal, the last massive structures in a universe that has faded to near uniformity. But that end is so far in the future that it's barely worth considering. For now, for timescales relevant to galaxies and stars and life, supermassive black holes are permanent fixtures of the cosmic landscape. They anchor galaxies, they regulate star formation, they serve as traces of cosmic history. And they do all of this with a stability and patience that offers profound comfort. Right now, as you rest, Sagittarius. A star sits at the center of our galaxy, 4 million solar masses of curved spacetime, visible only through its effects on nearby matter. Stars orbit it in predictable paths. Gas clouds occasionally fall into it, and it waits, patient and eternal, as it has waited for billions of years and will wait for billions more. Let that patience comfort you. Let the stability of these cosmic anchors ease your mind. The universe has structure, stability, permanence. At the heart of every large galaxy, a supermassive black hole marks the center, a lighthouse of gravity around which billions of stars revolve. These giants have been here longer than our sun, longer than our solar system, and they'll be here long after our sun has died. They're proof that the universe, despite its vast scales and deep time, has order. They're proof that even the most extreme objects follow predictable laws. They're proof that cosmic stability exists on scales we can barely imagine. And as you drift towards sleep, know that this stability holds. The supermassive black holes keep their vigil. The galaxies continue their stately rotations, and the universe unfolds according to the mathematics of curved spacetime, exactly as it should, exactly as it must. Perhaps nothing demonstrates the patient nature of black holes better than Hawking radiation, the quantum mechanical process through which black holes very, very slowly evaporate. Understanding this phenomenon offers a profound sense of peace about the ultimate fate of black holes and the deep connection between quantum mechanics and gravity. Hawking radiation is named after Stephen Hawking, who predicted its existence in 1974 by combining quantum field theory with general relativity. His calculations showed that black holes aren't completely black. They emit radiation with a temperature inversely proportional to their mass. Larger black holes are colder. Smaller black holes are hotter. All black holes, given enough time, will eventually evaporate completely. But the timescales involved are so vast that they make the current age of the universe seem like the blink of an eye. A black hole with the mass of our sun would have a temperature of about 6/100 billionths of a degree above absolute zero. At this temperature, it would take approximately 10 to the power of 67 years to evaporate completely. That's 10 million trillion years, a number so large it's essentially meaningless to our human minds. For more massive black holes, the evaporation time scales even longer. A supermassive black hole of 4 million solar masses, like Sagittarius A star at the center of our galaxy, would take roughly 10 to the power of 97 years to evaporate. A truly massive supermassive black hole of 100 billion solar masses would take about 2 times 10 to the power of 100 years. These timescales are so incomprehensibly long that it's worth pausing to appreciate what they mean. The universe is currently about 13.8 billion years old, or 10 to the power of 10 years. The last stars will burn out in perhaps 100 trillion years, 10 to the power of 14 years. After that, galaxies will continue to exist for a while as dead stellar remnants orbiting in the dark, But even these structures will eventually dissolve as stars are ejected from galaxies through gravitational interactions. This galaxy evaporation will take perhaps 10 to the power of 20 years. Even then, black holes will have barely begun their evaporation. They'll continue to exist, silent and dark, for timescales that make the entire stellar era of the universe seem brief. It's only in the unimaginably distant future, in what's sometimes called the black hole era, that Hawking radiation becomes significant. But here's what makes this beautiful. Black holes do eventually evaporate. They're not permanent features that will exist forever. Even though the timescales are beyond comprehension, the process is real, inevitable, and mathematical certainty. Quantum mechanics ensures that nothing, not even black holes, lasts forever. The universe will eventually return to a state of near uniformity, with all the matter that once existed having either been converted to radiation or escaped as Hawking radiation from evaporating black holes. The mechanism of Hawking radiation is subtle and often misunderstood. Hawking himself explained it with a simplified analogy involving virtual particle pairs appearing at the event horizon, but this explanation, while intuitive, isn't quite accurate. The real mechanism involves quantum fields in curved spacetime. Near a black hole, the intense curvature of spacetime affects quantum fields. In quantum field theory, what we call empty space is actually a quantum vacuum filled with field fluctuations. In flat spacetime, far from any massive objects, these fluctuations balance out, producing no net emission of particles. But near a black hole's event horizon, the curvature of spacetime is so extreme that it affects these quantum fluctuations in a way that produces real particles with positive energy that escape to infinity, while negative energy flows into the black hole, reducing its mass. This process is incredibly slow. The power emitted by a solar mass black hole through Hawking radiation is about 10 to the power of minus 28 watts. That's 10 septillionths of a trillionth of a watt. Far less power than a single photon of visible light carries. The black hole is radiating, but so faintly that it would be utterly impossible to detect even if we could position a detector right next to the event horizon. For supermassive black holes, the power is even lower. The temperature of Hawking radiation decreases with mass, and the power emitted decreases with the square of the mass. Sagittarius. A star radiates through Hawking radiation at a rate trillions of times smaller than a solar mass black hole. It's adding mass through the absorption of cosmic microwave background radiation far faster than it's losing mass to Hawking radiation. In the current universe, black holes grow slightly faster than they evaporate, making Hawking evaporation entirely negligible. But this will change. As the universe expands and cools, as stars die and the cosmic microwave background temperature drops, there will eventually come a time when black holes can no longer accrete anything. The universe will have cooled below the temperature of Hawking radiation for even supermassive black holes. At that point, these giants will begin, very slowly, to evaporate. The evaporation accelerates as the black hole shrinks. As mass decreases, temperature increases, and power increases. A black hole that has been slowly evaporating for most of its lifetime will spend its final stages evaporating much more rapidly. When a black hole shrinks to roughly the mass of a large asteroid, it will be hot enough to produce a cascade of particles and possibly end in a final burst of gamma rays. But even this dramatic ending, this final flash of a black hole's evaporation, represents the culmination of evaporation lasting longer than 10 to the power of 60 years. Recent theoretical work in 2023 and 2024 has refined our understanding of Hawking radiation. A study published in Physical Review Letters in 2023 by researchers at Radboud University showed that Hawking radiation can occur not just at the event horizon, but also far beyond it, due to the curvature of space-time. This research demonstrated that gravity and the curvature of space-time themselves cause radiation, not just the presence of an event horizon. This means that even objects without event horizons, like neutron stars or white dwarfs, might emit a form of Hawking-like radiation, though at even lower rates than black holes. This discovery suggests that everything in the universe may eventually evaporate through this quantum process, given enough time. Not just black holes, but all massive objects might slowly radiate away their mass energy over timescales of 10 to the power of 100 years or more. The universe's ultimate fate, trillions upon trillions of years in the future, might be a return to a nearly empty state, with all structure dissolved into diffuse radiation. But these timescales are so vast that they're essentially infinite from any practical perspective. For the entire future that we can meaningfully think about, for all the eons during which the universe will contain stars and galaxies and potentially life, Hawking radiation is negligible. It's a whisper, a quantum flutter at the edge of black holes, mathematically certain but practically irrelevant. And there's something deeply peaceful about this. It means that even the most extreme objects in the universe aren't eternal. Given enough time, everything returns to simplicity. The black holes that will eventually dominate the universe in mass will themselves eventually fade away, leaving nothing but faint radiation and iron spheres, the last remnants of dead stars that will themselves eventually decay through quantum tunneling on timescales of 10 to the power of 1,500 years or more. But we need not worry about these distant futures. For now, for all of cosmic time that matters to structure and complexity in life, black holes are effectively eternal. They're stable features of the universe that will outlast stars, outlast galaxies, outlast everything we know. And they fulfill this role with mathematical precision, following the equations of quantum field theory, in curved spacetime exactly as the mathematics predicts. The existence of Hawking radiation also reveals something profound about the nature of black holes and information. The radiation emitted by a black hole is thermal, at least to lowest order. It doesn't carry information about what fell into the black hole. This leads to the black hole information paradox. If all the information about matter that fell into a black hole is lost when the black hole evaporates, doesn't that violate quantum mechanics, which requires that information be preserved? This paradox has been one of the central problems in theoretical physics for decades. Various solutions have been proposed, including the possibility that information is somehow encoded in correlations in the Hawking radiation that are too subtle to detect with simple measurements, or that information is stored in a remnant left over after the black hole evaporates, or that information is transferred to another universe through the black hole. Recent work, particularly developments in holography and the ADS-CFT correspondence, suggests that information is preserved in subtle correlations in the Hawking radiation, resolving the paradox in a way that maintains both quantum mechanics and general relativity. But whatever the ultimate resolution of the information paradox, the essential fact remains. Black holes evaporate through Hawking radiation over timescales that dwarf the current age of the universe by factors too large to comprehend. This evaporation is gentle, patient, inevitable. It ensures that nothing in the universe is truly permanent, that even black holes will eventually fade away. As you rest tonight, picture a black hole in the far future of the universe. The stars have all died. The galaxies have dissolved. The universe is cold and dark, barely above absolute zero. And there, in this nearly empty space, a black hole sits, invisible and silent. It emits Hawking radiation at a temperature trillions of times lower than the cosmic microwave background that once filled the universe. Photons with wavelengths larger than galaxies slowly carry away its mass, one quantum at a time. This process continues for 100 million trillion years. The black hole shrinks, atom by atom, slower than anything we could possibly imagine. And eventually, after a span of time that makes the entire age of the universe seem instantaneous, the black hole evaporates completely, its last particles dispersing into the void. It's a peaceful ending, cosmic in its scope, gentle in its inevitability, and it demonstrates that the universe has a natural tendency toward simplicity. Given enough time, all structure dissolves, all complexity fades. Everything returns to a state of maximum entropy, of minimal information, of perfect equilibrium. But we're not there yet. We won't be there for timescales that are effectively infinite. For now, the black holes remain. They mark the deepest gravity wells in the universe. They anchor galaxies. They provide structure to the cosmos. And they whisper so faintly that we cannot hear, radiating away their mass in a quantum process so slow that it might as well not exist at all. Let this patience comfort you. Let the gentleness of Hawking evaporation, the near-infinite timescale of black hole decay, ease you toward rest. Nothing is truly permanent, but some things persist for so long that they might as well be eternal. Black holes will outlast everything, and even they will eventually fade away, not with a bang, but with the softest possible whisper, returning their mass to the universe one quantum at a time. Black holes serve as remarkably precise markers of cosmic time. Their predictable behavior, their stable evolution, and their role in the structure of the universe make them natural clocks measuring the passage of eons. Understanding how black holes function as timepieces offers insight into the deep structure of time itself. When two black holes merge, they emit gravitational waves with a characteristic signature that physicists call a chirp. The frequency of these waves increases as the black holes spiral closer together, rising from perhaps a few tens of hertz to several hundred hertz in the final fraction of a second before merger. This rising tone, when converted to sound waves, literally sounds like a bird's chirp rising in pitch. But this chirp carries information. The rate at which the frequency changes tells us about the masses of the merging black holes and their distance from Earth. The overall amplitude of the waves tells us how much energy was released in the merger. And, most remarkably, the details of the signal, including subtle features called overtones and the ring-down phase that follows the merger, reveal information about the final black hole's mass, spin, and even tests the predictions of general relativity itself. The first detection of gravitational waves from a black hole merger, GW1 Fimes during 914, occurred on September 14, 2015. The signal lasted about 1/5 of a second, sweeping from 35 Hz to 250 Hz. Analysis revealed that two black holes, with masses of about 29 and 36 times the Sun's mass, had merged to form a black hole of 62 solar masses. The missing 3 solar masses, equivalent to the mass energy of about 600 trillion kilograms, had been radiated away as gravitational waves. Think about that for a moment. 3 times the mass of our entire Sun, converted into pure gravitational radiation in less than a second. The power output in that brief instant exceeded the combined luminosity of all the stars in the observable universe. Yet this happened more than 1 billion light-years away, and by the time the gravitational waves reached Earth, they were so attenuated that they caused our 4-kilometer-long detectors to move by less than 1/10,000th the diameter of a proton. This is measurement at a level of precision that borders on the absurd, and yet we can do it. 10 years later, in January 2025, LIGO detected another, remarkably similar event designated GW250 unwind 4. Two black holes, again with masses between 30 and 40 solar masses, again about 1.3 billion light-years away, merged to create a final black hole. But this time, thanks to a decade of improvements to the detectors, the signal was stunningly clear. The signal-to-noise ratio reached 80 compared to 26 for the original GW150 detection. This exceptional clarity allowed scientists to measure something they had never been able to before, the ring-down phase of the black hole merger. After two black holes merge, the resulting black hole doesn't immediately settle into a perfect spherical shape. It rings like a bell, oscillating in what physicists call quasi-normal modes. These oscillations produce gravitational waves with specific frequencies and decay rates that depend only on the final black hole's mass and spin. For the first time with GW25114, scientists could identify not just the fundamental frequency of this ringing but also the first overtone, a higher frequency component similar to the overtones that give musical instruments their characteristic sounds. This detection provided the most precise test yet of general relativity under extreme conditions and confirmed with 99.9999% confidence Stephen Hawking's famous area theorem that the total surface area of the event horizons of merging black holes must increase or stay the same, never decrease. This theorem connects to deep concepts in physics. The area of a black hole's event horizon is proportional to its entropy, a measure of disorder and information content. The increase in area reflects the second law of thermodynamics, which states that entropy always increases in closed systems. Black holes obey thermodynamics just like everything else in the universe. They have temperature, entropy, and they radiate. They're not exempt from the fundamental laws of physics. They're subject to them, predictably and measurably. Since that first detection in 2015, the LIGO Virgo Kagra network has grown dramatically in capability. During the first 3 observing runs, spanning 23 months of total observation time between 2015 and 2020, the detectors recorded 90 gravitational wave events. In the 4th observing run, which began in May 2023 and concluded in November 2025, the network detected 200 candidate events in approximately the same amount of observing time. That's more than double the detection rate, reflecting both improved detector sensitivity and our expanding catalog of cosmic collisions. On March 19, 2025, the network recorded its 200th gravitational wave candidate of the 4th observing run. The detections have become so routine that candidate events are now announced to the astronomical community within minutes of detection, allowing telescopes around the world to quickly search for any associated electromagnetic signals from the same source. Most gravitational wave events are purely gravitational, producing no light or other electromagnetic radiation. But when neutron stars are involved, the collision can produce bursts of gamma rays, optical light, and radio waves, creating what astronomers call a multi-messenger event. The discoveries from this 4th observing run have revealed surprising diversity in black hole properties. In October 2024, LIGO detected 2 events, designated GW2441011 and GW2411110, that showed unusual spin configurations. The black holes in these systems were rotating rapidly and at odd angles to their orbital planes, suggesting they formed through what physicists call hierarchical mergers. These are black holes that themselves formed from earlier black hole mergers in dense stellar environments like globular clusters or the centers of galaxies. This discovery paints a picture of black hole families where black holes merge and the products of those mergers later merge with other black holes, creating ever larger black holes through generations of collisions. It's a cosmic genealogy written in gravitational waves, where we can trace the ancestry of black holes back through multiple generations of mergers. Another remarkable discovery came in May 2023, shortly after the start of the fourth observing run. The system GW23529 involved the collision of a neutron star with a compact object between 2.5 and 4.5 solar masses. This mass range is intriguing because it falls in what astronomers call the mass gap, a range where very few objects have been found. We don't know if these mass gap objects are extremely massive neutron stars pushed to the limit of what neutron degeneracy pressure can support, or if they're lightweight black holes. The gravitational wave signal alone can't tell us. But the increasing number of such detections suggests that this mass gap isn't as empty as we once thought. The fourth observing run also announced one potentially remarkable candidate. GW23123, described as likely the highest mass binary black hole merger observed to date. The masses of the component black holes in this system push into regimes where stellar evolution models struggle to predict how such massive objects could form. These discoveries are rewriting our understanding of how massive stars live and die and what remnants they leave behind. Each of these detections is a clock, marking the moment when two black holes, having orbited each other perhaps for millions or billions of years, finally came together. The gravitational waves carry precise information about when the merger happened, where it happened, how massive the black holes were, how fast they were spinning, and even subtle details about how their spins were oriented relative to their orbital plane. And this is just the beginning. The fifth observing run is expected to begin in late 2025 or 2026 with even better sensitivity. LIGO India, a third LIGO detector, being built in India, will eventually join the network, improving our ability to locate gravitational wave sources in the sky. Future detectors, like the planned Einstein telescope in Europe and the Cosmic Explorer in the United States, promise sensitivities 10 times greater than current instruments, potentially allowing us to detect black hole mergers anywhere in the observable universe. Each gravitational wave detection is a moment captured in time, a cosmic clock ticking once to mark a merger. But the black holes themselves are also timekeepers in a broader sense. Their predictable behavior, their stable existence, their patient spirals toward eventual collision, all mark the passage of time on cosmic scales. They're like the hands of a clock measuring not seconds or hours, but millions and billions of years. The orbit of a binary black hole system decays with exquisite precision, following equations that can be solved exactly. Given the masses and orbital parameters, we can calculate precisely how long it will take for the black holes to merge down to the fraction of a second. The universe operates like clockwork, even at its most extreme. And when black holes do merge, they mark time in another way, through their gravitational wave signal. The frequency of the waves increases in a completely predictable way as the black holes spiral closer. The final chirp, the ring down, the decay to a stable final state, all follow precise mathematical rules. It's a cosmic metronome, marking time with gravitational waves, and we've learned to read that rhythm. As you rest tonight, picture those gravitational waves passing through you. Right now, space itself is rippling with echoes of black hole mergers that happened billions of years ago. The waves are faint, far too faint to feel, but they're there, passing through your body, through the earth, through everything, carrying information about cosmic collisions from the deep past. These ripples in space-time are time itself made tangible, the universe's way of recording and broadcasting its most dramatic events. And somewhere out in space, right now, two black holes are spiraling toward each other, their orbit decaying through gravitational wave emission, counting down the billions of years until they finally merge. When they do, they'll send out another chirp, another gravitational wave signal, marking another moment in cosmic time. And, if humanity still exists, if our detectors are still operating, we'll hear that signal too, adding another tick to the cosmic clock that black holes keep for us. Let this rhythm comfort you. Let the predictability of black hole mergers, the precision of gravitational waves, the clockwork nature of these cosmic collisions ease you toward rest. The universe keeps time. Black holes mark it. And the mathematics we've developed let us read those cosmic clocks and understand the deep time structure of the cosmos. The detection of gravitational waves has transformed black hole astronomy from a purely theoretical enterprise into an observational science. Before 2015, we had strong indirect evidence for black holes from the motion of stars and gas around invisible objects, but we had never directly observed a black hole's gravitational effects propagating through space. The detection of gravitational waves changed everything, opening a new window on the universe and revealing a population of black holes we didn't know existed. The journey to detecting gravitational waves began in the early 20th century with Einstein's general theory of relativity. The theory predicted that accelerating masses should produce ripples in space-time that propagate outward at the speed of light. But Einstein himself was skeptical that these waves would ever be detected. They're incredibly weak, and the technology needed to measure them seemed impossibly far out of reach. For decades, physicists worked to develop that technology anyway. The basic concept of a gravitational wave detector is elegant. Use laser interferometry to measure tiny changes in distance between widely separated masses. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction. By splitting a laser beam and sending it down two perpendicular arms, then recombining the beams, you can detect these tiny distortions through interference patterns in the recombined light. But the distortions are absurdly small. A gravitational wave from even a relatively nearby black hole merger might change the length of a 4-kilometer detector arm by less than 1,000th the diameter of a proton. That's like measuring the distance to the nearest star to within the width of a human hair. The technical challenges were enormous. Isolating the detectors from seismic noise, controlling quantum noise in the laser light, suspending the mirrors in near-perfect vacuums, accounting for thermal vibrations. Every possible source of noise had to be identified and suppressed. The LIGO detectors, built in the 1990s and early 2000s, operated for years without detecting anything. The initial LIGO observing runs from 2002 to 2010 saw no gravitational waves. The signals were simply too weak and the detectors weren't sensitive enough. But physicists had always known this might happen. Initial LIGO was a pathfinder, a proof of concept, a way to work out the engineering challenges before building advanced LIGO with 10 times better sensitivity. The upgrade to advanced LIGO began in 2010 and took 5 years. When advanced LIGO turned on in September 2015, physicists expected it would take months or years to detect the first gravitational wave signal. Instead, they detected one within days. On September 14, 2015, just 2 days after advanced LIGO began its first observing run, both detectors saw the same signal. A chirp rising in frequency and amplitude, lasting 0.2 of a second, perfectly matching the predictions for two merging black holes. The detection was so clear, so obviously a real signal, that some team members initially thought it might be a blind injection, a fake signal inserted to test the analysis pipeline. But it wasn't. It was real. Two black holes, 30 and 35 times the mass of the Sun, had merged 1.3 billion years ago, and the gravitational waves from that event had just reached Earth. The signal was named GW150991 Force, marking the date of detection, September 15, 2014 in Coordinated Universal Time. This detection confirmed not just the existence of gravitational waves, but also the existence of stellar mass black holes in binary systems. Before LIGO, the heaviest stellar mass black holes we knew about were around 20 solar masses. The 30 and 35 solar mass black holes in GW150914 were heavier than any stellar remnant previously known, suggesting that massive stars can form more massive black holes than astronomers had predicted. It was the first hint that LIGO would reveal a population of black holes different from what X-ray astronomy had found. And that's exactly what happened. As more detections accumulated, a picture emerged of black hole masses clustering around 30 solar masses, heavier than most black holes detected through X-ray emission from binary systems. This difference likely reflects selection effects. X-ray binaries require ongoing mass transfer from a companion star, which favors lower mass black holes in certain orbital configurations. Gravitational wave detections see all merging black hole binaries, regardless of whether they're actively accreting matter, giving us an unbiased census of the black hole population. The detections also revealed that black hole mergers happen far more frequently than anyone expected. Initial predictions suggested LIGO might detect a few black hole mergers per year. Instead, during the third observing run in 2019 to 2020, LIGO and Virgo were detecting black hole mergers roughly once every 5 days. In the fourth observing run, starting in 2023, the rate increased to approximately 1 detection every 2 to 3 days. The universe is full of merging black holes, far more than pre-LIGO estimates suggested. Each detection adds to our understanding. The spin measurements tell us about black hole formation mechanisms. Black holes that form from stellar collapse should have spins aligned with the orbital plane of the binary system. Black holes that formed through dynamical capture in dense stellar environments might have spins misaligned from the orbital plane. By measuring spin orientations across many systems, we can begin to understand whether most black hole binaries formed through stellar evolution or through dynamical interactions. The masses of the detected black holes also constrain stellar evolution models. Stars more massive than about 150 solar masses are thought to be unstable to pair instability supernovae, explosions so powerful they completely destroy the star without leaving any remnant. This creates a predicted mass gap where black holes between about 50 and 120 solar masses shouldn't exist. But LIGO has detected systems in this gap, including GW190521, where the more massive black hole had a mass of about 85 solar masses. These detections suggest either that pair instability supernovae don't work exactly as predicted, or that these black holes form through mergers of smaller black holes rather than direct stellar collapse. Some gravitational wave sources have also been detected in electromagnetic light, creating multi-messenger observations. The event GW170817, detected in August 2017, came from the merger of two neutron stars. Within seconds of the gravitational wave detection, gamma-ray satellites detected a short gamma-ray burst from the same direction. Within hours, optical telescopes found a new light source in the galaxy NGC 4993, a kilonova powered by the radioactive decay of heavy elements synthesized in the merger. This single event confirmed that neutron star mergers are the source of short gamma-ray bursts and a major production site for heavy elements like gold and platinum. The ability to detect both gravitational waves and electromagnetic signals from the same source opens new possibilities for astronomy. Gravitational waves tell us about the masses and spins of the compact objects, independent of distance. Electromagnetic observations tell us about the environment, the matter surrounding the merger, and allow precise distance measurements through the identification of the host galaxy. Together, they provide a complete picture that neither technique could provide alone. The detection of gravitational waves has also enabled new tests of general relativity. The waves must propagate at the speed of light, as general relativity predicts. Their frequency evolution must match the predictions from numerical relativity simulations. The polarization of the waves must match general relativity's predictions for the two allowed polarization states. So far, every test has confirmed general relativity. The theory, worked out by Einstein more than a century ago, describes gravitational waves from black hole mergers with perfect accuracy. But perhaps the most profound impact of gravitational wave detection is simply this: it works. The universe really does produce gravitational waves. Black holes really do merge, and we can detect and study these events, extracting detailed information about cosmic phenomena happening billions of light years away. What was once purely theoretical is now observational. What was once invisible is now seen, not with light, but with gravity itself. As you drift towards sleep, let this sink in. The universe is transparent to gravitational waves in a way it isn't to light. Light gets absorbed, scattered, redshifted, but gravitational waves pass through matter and energy essentially unimpeded. They propagate from the most distant reaches of the universe to Earth without distortion, carrying pristine information about their sources. Every black hole merger that's ever happened has sent gravitational waves rippling through the universe. And those waves are still traveling, still carrying their information, waiting for detectors sensitive enough to capture them. Right now, there are gravitational waves from millions of black hole mergers passing through your body. Most are far too weak to detect, but they're there, invisible ripples in space-time carrying the news of cosmic catastrophes from across the universe. And every second, somewhere in the observable universe, black holes are merging, adding new waves to this cosmic ocean of gravitational radiation. The universe is alive with these signals. It's singing if you have the right ears to hear. And we finally built those ears. We've taught ourselves to listen to space-time itself, to hear the universe's most dramatic events unfold in gravitational waves. It's peaceful, in a way, knowing that we've reached this level of understanding, that we can measure things so small and understand events so far away. Let that understanding comfort you as you rest. The universe makes sense. Its most extreme phenomena follow mathematical laws we can understand and predict, and those phenomena produce signals we can detect and decode, revealing the deep structure of space-time and matter. We live in an age of gravitational wave astronomy where black holes have gone from theoretical curiosities to routinely observed phenomena. The universe has opened itself to us in a new way, and we're only beginning to explore what that window reveals. Black holes are, by definition, black. They emit no light of their own. The event horizon is a perfect absorber, capturing all electromagnetic radiation that crosses it, allowing none to escape. This darkness, this perfect blackness, is one of a black hole's most fundamental properties. But rather than being threatening, this darkness has a protective quality, shielding the universe from whatever strange physics operates near the singularity. The reason black holes are black is straightforward. Light cannot escape from within the event horizon. Once light crosses that boundary, all future light paths lead inward toward the singularity. There's no trajectory, no combination of direction and velocity that will allow light to climb back out of the gravitational well. The escape velocity at the event horizon equals the speed of light, and since nothing can move faster than light, nothing can escape. This creates the characteristic appearance of a black hole, a perfectly dark sphere in space, visible only as a shadow against any background light. when the Event Horizon Telescope imaged the black holes in Messier 87 and in our own Sagittarius A star. What they captured was essentially a black hole's shadow, the region where light rays are captured or bent around the black hole, creating a dark circle surrounded by a bright ring of light from the accretion disk. The darkness extends to all forms of radiation, not just visible light. Radio waves, infrared, ultraviolet, X-rays, gamma rays, everything in the electromagnetic spectrum is trapped if it crosses the event horizon. The black hole is perfectly black across all wavelengths, a void in the electromagnetic spectrum, a place where no radiation emerges from inside. But this darkness serves a crucial function. It protects the external universe from whatever happens inside. According to general relativity, the density at the center of a black hole becomes infinite at a point called the singularity. At the singularity, space-time curvature becomes infinite, tidal forces become infinite, and our equations break down. We don't know what physics describes conditions at a singularity. General relativity itself fails there, but we don't need to know because the singularity is hidden behind an event horizon. This is known as the cosmic censorship hypothesis, proposed by Roger Penrose. Nature abhors naked singularities. Every singularity is clothed in an event horizon that prevents it from affecting the external universe. Whatever strange, possibly chaotic physics operates at singularities, it's sealed away, quarantined behind a boundary that light and information cannot cross. This quarantine has profound implications. It means that the breakdown of our understanding of physics at singularities doesn't leak out to affect the wider cosmos. The universe remains predictable, describable by general relativity and quantum field theory, even though these theories fail at singularities. The event horizon is a firewall, protecting normal spacetime from the regions where our physics breaks down. Some theoretical physicists have questioned whether information really is sealed behind event horizons or whether there might be subtle mechanisms by which information escapes. Recent work on the black hole information paradox, particularly developments involving the holographic principle and concepts like entanglement islands and quantum extremal surfaces, suggests that information about matter that falls into a black hole is preserved and eventually returns to the outside universe through correlations in the Hawking radiation. The Page curve, named after physicist Don Page, describes how the entropy of Hawking radiation should evolve if information is preserved. Initially, as a black hole emits radiation, the entropy of that radiation should increase. But about halfway through the evaporation process, the curve should turn over and the entropy should begin to decrease, approaching zero as the black hole completely evaporates. This would indicate that information is being returned to the radiation, encoded in subtle correlations between the particles. Recent theoretical work in 2020 and beyond has shown how semi-classical calculations, including quantum corrections, can reproduce the Page curve, suggesting that information is indeed preserved, consistent with quantum mechanics. The resolution appears to involve quantum entanglement between the interior and exterior of the black hole, mediated by regions called entanglement islands that allow information to be encoded in the structure of spacetime itself. A December 2024 study suggested that these quantum correlations in spacetime might even leave detectable signatures in gravitational waves from black hole mergers. These imprints would be incredibly subtle, far below the sensitivity of current detectors, but future gravitational wave observatories might be able to detect them, providing experimental evidence for how black holes preserve and release information. All of this theoretical work suggests that event horizons aren't quite the perfect one-way boundaries they appear to be classically. Quantum mechanics introduces subtle effects that allow information to slowly leak back out over the vast timescales of Hawking evaporation. But for all practical purposes, for anything happening on human or even stellar timescales, the event horizon remains an effective barrier. What goes in doesn't come back out, at least not in any form we could recognize. This effective darkness, this sealing off of the black hole interior, has a comforting quality. It means the universe has built-in safety mechanisms. The regions where our understanding breaks down are naturally hidden away. We don't have to worry about naked singularities appearing in the universe, disrupting causality, or creating unpredictable chaos. The cosmos has structure, boundaries, rules that confine the unknowable to specific, sealed-off regions. The darkness of black holes also creates a kind of simplicity. From outside, all black holes with the same mass, spin, and charge are identical. The no-hair theorem in general relativity states that these three parameters completely specify a black hole. Any other information about how the black hole formed, what matter fell into it, what its history was, is erased. All black holes are smooth, featureless, described by just mass, spin, and possibly charge. This simplicity is beautiful. Despite the complexity of stellar evolution, the chaos of stellar death, the randomness of what matter might fall into a black hole over its lifetime, the end result is an object described by just a few numbers. It's a kind of cosmic reset, a return to simplicity from complexity, an erasure of history leaving only the essential parameters. And yet, quantum mechanics suggests this erasure isn't quite complete. The information about what fell in is preserved, encoded somehow in the structure of the event horizon and in the correlations between Hawking radiation particles. The black hole remembers, but in a way we're only beginning to understand, in subtle quantum properties rather than classical features. The unwind darkness also provides a backdrop against which we can see other light more clearly. The bright accretion disks around black holes shine brilliantly precisely because they're contrasted against the perfect blackness of the event horizon. The darkness makes the light more vivid, the shadows more defined. It's like the black background of space making the stars visible. The void enhances what it surrounds. As you rest, think about darkness, not as an absence, but as a presence. The darkness of black holes is an active feature, a property, a shield that protects and simplifies. It's the universe's way of containing the unknowable, of keeping the breakdown of physics confined to specific regions, of ensuring that the wider cosmos remains comprehensible. And in that darkness, there's peace. The perfect blackness of an event horizon is complete, total, absolute. No light escapes, no information directly emerges. It's a final boundary, an ultimate limit, a line that cannot be uncrossed from the inside. And knowing that such boundaries exist, that the universe has edges and limits and rules, provides a sense of structure and order. The universe contains its mysteries within event horizons, behind veils of darkness, protecting itself from the regions where our understanding fails. And we, on the outside, can study black holes mathematically, detect them observationally, understand their effects on space-time and matter, all without having to grapple with the infinite densities and broken physics at singularities. The darkness shields us, allowing us to understand black holes as astrophysical objects without requiring us to solve the deepest problems of quantum gravity. Let that protection comfort you. The universe has boundaries, both physical and conceptual, that keep things orderly. The darkness of black holes is one such boundary, a limit beyond which light cannot return, but within which the unknown is contained. It's a peaceful darkness, a protective darkness, a darkness that enables the rest of the universe to shine. Black holes exist on timescales that dwarf human comprehension. Their formation, evolution, and eventual fate unfold over periods measured not in years or centuries, but in billions and trillions of years, and ultimately in numbers so large they become meaningless. Understanding these vast timescales provides a profound sense of perspective about our place in the cosmos and the patient unfolding of the universe. Consider the life of a massive star that will eventually become a black hole. The star forms from a collapsing cloud of gas over the course of perhaps a few 100,000 years, then burns hydrogen in its core for 10 to 20 million years, depending on its mass. More massive stars burn faster, exhausting their fuel more quickly. When the hydrogen runs out, the star begins burning helium, then heavier elements in successive stages, each stage shorter than the last. The final stages of a massive star's life happen quickly by stellar standards. Carbon burning lasts perhaps 1,000 years. Oxygen burning takes about a year. Silicon burning takes a week. Then, when the core tries to fuse silicon into iron, the process fails because iron nuclei are more stable than their components, and fusion no longer releases energy. The core collapses catastrophically in less than a second, either bouncing and producing a supernova, or, for the most massive stars, collapsing directly to a black hole without an explosion. So from the star's perspective, black hole formation is the culmination of millions of years of steady nuclear burning, followed by seconds of catastrophic collapse. But from the black hole's perspective, its existence has only just begun. The black hole that forms from the stellar collapse will persist for timescales that make the star's lifetime seem infinitesimally brief. A stellar mass black hole of, say, 10 solar masses will survive essentially unchanged for longer than the current age of the universe. Black holes don't age in any meaningful sense. They don't decay or deteriorate. They simply exist, patient and eternal, maintaining their properties indefinitely unless they merge with another black hole or accrete additional mass. The galaxy in which the black hole sits will evolve around it. Stars will form and die. The galaxy might merge with other galaxies, undergo periods of intense star formation and quiescent dormancy. The supermassive black hole at the galaxy's center will grow through accretion and mergers. But the stellar mass black hole, if left to itself, remains essentially unchanged, a stable point in a changing cosmos. On even longer timescales, the structure of galaxies themselves begins to break down. Stars are occasionally ejected from galaxies through gravitational interactions, particularly during galaxy mergers. Over timescales of 10 to the power of 18 to 10 to the power of 20 years, these interactions will cause galaxies to evaporate, with most stars flung into intergalactic space and a small fraction falling into the central, supermassive black hole. But even this timescale is brief compared to the lifetime of black holes themselves. The evaporation through Hawking radiation that we discussed earlier takes 10 to the power of 67 years for a solar mass black hole, far longer than the time needed for galaxy evaporation. Black holes will be among the last macroscopic structures remaining in the universe, long after stars have burned out and galaxies have dispersed. During what cosmologists call the black hole era of the universe, from about 10 to the power of 40 years to 10 to the power of 100 years after the Big Bang, black holes will dominate the mass of the universe. Everything else, all the stars and planets and gas and dust, will have decayed, radiated away, or been consumed. Only black holes and their Hawking radiation will remain, and even the black holes will eventually evaporate. A solar mass black hole takes 10 to the power of 67 years to evaporate completely. A black hole with the mass of Sagittarius, a star, 4 million solar masses, takes about 10 to the power of 97 years. The largest supermassive black holes, hundreds of billions of solar masses, take 10 to the power of 100 years or more. These timescales are so vast that they're difficult to comprehend. To put them in perspective, the current age of the universe is about 14 billion years, or 1.4 times 10 to the power of 10 years. The time until the last stars burn out is perhaps 100 trillion years, or 10 to the power of 14 years. Even the longest-lived stars, the smallest red dwarfs, will exhaust their fuel in a few trillion years. After that, the universe will be dark, lit only by the occasional flare as matter falls into black holes, or white dwarfs and brown dwarfs occasionally collide. But black holes will persist through all of this. They'll outlast the stars by factors of 10 to the power of 50 or more. They'll be the only large-scale structures remaining, slowly evaporating through Hawking radiation, releasing their mass energy back into the universe over timescales that make the entire stellar era seem like an eye blink. And what happens after the last black hole evaporates? The universe will be filled with a diffuse gas of elementary particles, photons, neutrinos, electrons, positrons, moving through an ever-expanding space that's colder and emptier than anything we can currently imagine. The temperature will be incomprehensibly close to absolute zero. Distances between particles will be astronomical. The universe will have reached a state of maximum entropy, with all structure dissolved, all information effectively lost to the expansion. This is sometimes called the heat death of the universe, though it's more accurate to call it a cold death. It's the ultimate fate predicted by thermodynamics. All systems evolve toward maximum entropy, toward maximum disorder, toward equilibrium. And the final equilibrium state of the universe is empty, cold, and featureless, with all the matter and energy that once made up stars and galaxies and black holes dissipated into radiation or elementary particles. But this end is so far in the future that it's effectively forever. From our current position, 14 billion years after the Big Bang, we're still in the very early universe, cosmologically speaking. The era of stars and galaxies, the time when structure and complexity exist, will last for at least trillions of years, probably hundreds of trillions of years when you include the lifetimes of the longest-lived stars. And black holes mark the passage of this deep time. They're witnesses to cosmic history, forming when massive stars die and persisting long after everything else has faded. They're like cosmic monuments, marking points in space-time where matter became so concentrated that it warped space to the breaking point. And they'll be the last monuments standing, the final large structures in a universe that's slowly forgetting everything else. This perspective, this sense of deep time, can be comforting. It reminds us that the universe operates on scales far beyond human concerns. Our lives are brief flashes in cosmic time, as are the lives of our civilizations, our species, even our planet and sun. But the universe itself continues, patient and eternal, following the inexorable logic of thermodynamics and gravity toward its ultimate fate. Black holes embody this patience. They don't rush, they don't hurry, they simply exist, marking time, measuring eons, bearing witness to the slow evolution of the cosmos. And in their patience, in their eternal stability, punctuated by only the most gradual change, they offer us a model of persistence, of duration, of existing in deep time. As you rest tonight, let yourself feel small in the best possible way. You're a brief pattern of organized matter, a temporary eddy in the flow of entropy, a complex structure that emerged for a moment in cosmic history before dissolving back into simpler forms. Your existence is improbable, precious, and temporary. But the universe that contains you is vast and patient, and the black holes scattered throughout it will endure long after you, long after your species, long after your world has vanished. And there's peace in that. Not the peace of insignificance, but the peace of being part of something much larger, something that will continue long after you're gone. The black holes will keep their vigil, the universe will evolve according to its laws, and the deep time of cosmic history will continue to unfold, patient and inexorable, exactly as the mathematics predicts it must. Let that vastness and that patience ease you into sleep. You exist in a universe of deep time, where black holes mark billions of years as casually as we mark seconds, where the evolution of galaxies takes longer than we can meaningfully comprehend, where the ultimate fate of everything won't be reached for timescales that make the current age of the universe seem like nothing at all. It's overwhelming, yes, but also deeply peaceful. The universe has time. So much time. More time than we could ever need, more time than we could ever imagine. And in that abundance of time, there's room for everything, including this moment, this breath, this peaceful descent into rest. At the heart of our understanding of black holes lies mathematics, not the complicated calculations and computer simulations, but the elegant, fundamental equations that describe how gravity curves spacetime and how matter responds to that curvature. These equations, remarkably simple in their essential form, predict the existence and behavior of black holes with perfect precision. Understanding this mathematical foundation offers a profound sense of peace about the orderly nature of the universe. Einstein's field equations, the core of general relativity, can be written in a deceptively compact form. They relate the curvature of spacetime on the left side of the equation to the distribution of mass and energy on the right side. Mass and energy tell spacetime how to curve. Spacetime tells matter how to move. It's a beautiful, self-consistent description of gravity as geometry rather than force. From these equations, Carl Schwarzschild found the first exact solution describing a black hole in 1916, just months after Einstein published General Relativity. Working on the Eastern Front during World War I, Schwarzschild derived a solution describing the spacetime around a spherically symmetric, non-rotating mass. His solution revealed a critical radius, now called the Schwarzschild radius, where the geometry changes fundamentally. Inside this radius, all paths lead inward. Outside, escape remains possible. The Schwarzschild radius is given by a wonderfully simple formula: R equals 2gm divided by c squared, where g is Newton's gravitational constant, m is the mass, and c is the speed of light. For our Sun, this works out to about 3 kilometers. For Earth, about 9 millimeters. For a supermassive black hole of 4 million solar masses, about 12 million kilometers. This simplicity is striking. Despite the complexity of general relativity, despite the non-linear nature of Einstein's equations, the Schwarzschild radius can be calculated with basic algebra. You can compute it on a calculator in seconds. And yet, this simple calculation tells you the size of the event horizon, the point of no return for light and matter, for any non-rotating, uncharged black hole of any mass. For rotating black holes, the solution becomes more complex. Roy Kerr found the exact solution for a rotating black hole in 1963, nearly 50 years after Schwarzschild. The Kerr solution is more complicated mathematically, involving additional parameters for angular momentum and featuring an ergosphere outside the event horizon where spacetime is dragged along with the black hole's rotation. But even this solution is exact, analytical, describable in closed form without needing numerical simulations. These exact solutions mean that if you know the mass and spin of a black hole, you know everything about its spacetime geometry. You can calculate exactly where the event horizon is, where the ergosphere extends to, how time flows at any distance from the black hole, how light paths bend in its vicinity. The entire geometry is determined, unique, calculable. This predictability extends to black hole mergers. When two black holes spiral toward each other, the space-time geometry becomes too complex to describe with analytical solutions. Physicists must use numerical relativity, solving Einstein's equations with supercomputers. But even these numerical solutions are completely deterministic. Given the initial masses, spins, and orbital parameters, the simulation produces a unique gravitational wave signal, a unique final black hole, mass, and spin. The mathematics leaves no room for randomness or uncertainty beyond quantum mechanical effects. The gravitational waves themselves obey a wave equation derived from Einstein's field equations. In the limit where the waves are weak and far from their source, this equation is linear and relatively simple to solve. The solutions are plane waves traveling at the speed of light with two possible polarizations, stretching and squeezing space in perpendicular directions as they pass. All of this comes directly from the mathematical structure of general relativity. The power radiated in gravitational waves from a binary system follows a clear formula known as the quadrupole formula, derived by Einstein himself. The power increases dramatically as the objects get closer, scaling as the fifth power of the orbital frequency. This is why binary black holes emit relatively little gravitational wave power when they're widely separated, but radiate enormous energy in the final moments before merger. The mathematics predicts exactly how the orbit decays, exactly how the frequency increases, exactly when the final plunge will occur. Even the information paradox, that deep puzzle about whether information is lost when black holes evaporate, is fundamentally a mathematical question. It arises from the apparent conflict between two mathematical frameworks: the unitarity of quantum mechanics, which requires information preservation, and the thermal nature of Hawking radiation, which appears to destroy information. The proposed resolutions involving holography and entanglement islands are themselves mathematical, demonstrating that suitably careful calculation can reconcile these frameworks. There's something deeply comforting about this mathematical predictability. Black holes aren't mysterious in the sense of being arbitrary or unknowable. They're mysterious in the sense that they push the boundaries of our physics, but within general relativity, they're completely determined by a few parameters and described by exact mathematical solutions. They're the most predictable, least arbitrary objects in the universe. Compare this to, say, weather on Earth. Weather systems involve turbulent fluid dynamics, chaotic behavior, sensitivity to initial conditions. We can simulate weather, but small uncertainties grow exponentially, limiting our predictive power to days or weeks. Black holes, by contrast, are described by equations that contain no chaos, no turbulence in their solutions. They're smooth, predictable, mathematical certainties. Or compared to quantum mechanics, with its inherent randomness, its probabilistic predictions, its uncertainty principles. Black holes, at least classically, have none of this. Their evolution is deterministic, their properties precisely defined, their behavior exactly calculable. They represent a realm where classical physics, specifically general relativity, reaches its most extreme application but remains completely predictive. The simplicity of black hole physics is encapsulated in the no-hair theorem, which states that black holes are completely characterized by just their mass, spin, and electric charge. All other information, all the complexity of how the black hole formed and what matter fell into it, is erased, leaving only these three numbers. This radical simplification means that from outside, all black holes with the same mass, spin, and charge are absolutely identical, indistinguishable, even in principle. This is unlike anything else in nature. Two stars with the same mass, composition, and rotation rate might seem similar, but will have countless differences in detail. But two black holes with the same mass, spin, and charge are literally the same object mathematically, described by the exact same solution to Einstein's equations. The black hole is the Platonic ideal made, real, the mathematical abstraction existing in physical space. Recent observations have confirmed these mathematical predictions with remarkable precision. The gravitational wave signal from GW2 5-1114 matched the predictions of numerical relativity so well that physicists could test subtle aspects of general relativity like the ring-down overtones and Hawking's area theorem. The Event Horizon Telescope, images of black holes matched simulations based on Einstein's equations. Every test confirms that the mathematics accurately describes reality. This agreement between mathematics and observation isn't guaranteed. We could live in a universe where the elegant equations give only approximate descriptions, where black holes don't quite match the predictions, where subtle deviations hint at new physics. But so far, in every test we've performed, general relativity describes black holes perfectly. The mathematics works. The universe, at least in this domain, operates exactly as the equations say it must. There's profound peace in this realization. The universe isn't arbitrary. It follows rules, mathematical rules, that we can discover and test and confirm. Black holes, the most extreme objects we know, are perfect exemplars of this. They do exactly what the mathematics predicts, no more, no less. They're not mysterious exceptions to physical law, they're perfect embodiments of it. As you rest, let this mathematical order comfort you. The universe is comprehensible. Its most extreme phenomena can be described with equations simple enough to write on a page. Those equations make predictions we can test and confirm. And black holes, far from being chaotic or unknowable, are the most predictable, most mathematical objects in existence, perfect geometric solutions to Einstein's equations floating in space. Let the elegance of the Schwarzschild radius formula ease you towards sleep. Let the predictability of gravitational waves, the deterministic evolution of merging black holes, the mathematical certainty of it all, provide a foundation of order in the cosmos. We live in a universe of laws, a universe where mathematics describes reality, where even black holes, the deepest gravity wells imaginable, follow rules we can understand and write down. That's serene. That's peaceful. That's a reason to rest easy, knowing the universe makes sense, knowing that mathematics reveals its deepest truths, knowing that black holes, for all their power and strangeness, are ultimately mathematical objects as pure and predictable as circles or spheres. The universe is rational, and in that rationality, there's peace. We've journeyed together through the serene nature of black holes, exploring their patient formation, their eternal existence, their mathematical beauty, and their role as timekeepers and anchors of the cosmic structure. What we've discovered is that these objects, so often portrayed as violent and destructive, are actually paragons of stability, predictability, and elegant simplicity. Black holes form through processes that can be gentle, creating new objects without catastrophic explosions. They mark boundaries in space-time with perfect geometric precision. They demonstrate that time is relative, flexible, accommodating different experiences without contradiction. They anchor galaxies, providing structure to the universe for billions of years. They whisper through Hawking radiation on timescales so vast they're effectively eternal. They emit gravitational waves that let us hear the universe in a new way, detecting cosmic collisions with mathematical precision. The darkness of event horizons protects the external universe from the breakdown of physics at singularities. The deep time of black hole evolution puts our brief lives in perspective, reminding us we're part of something vastly larger and longer-lived than ourselves. And the mathematics describing black holes is elegant and exact, proving that even the universe's most extreme phenomena follow comprehensible rules. Through it all, black holes demonstrate patience. They don't rush. They exist on timescales measured in billions and trillions of years. They evolve slowly, predictably, following the inexorable mathematics of general relativity. They're witnesses to cosmic history, marking where massive stars once burned, where galaxies collided, where space-time curves most severely. And they'll outlast almost everything else. Long after our sun has exhausted its fuel, after our galaxy has merged with Andromeda, after the last stars have burned out and the universe has faded to near uniformity, black holes will remain. They'll be the last large structures, slowly evaporating through Hawking radiation, returning their mass to the universe one quantum at a time over timescales that dwarf the current age of the cosmos. There's comfort in this longevity. Black holes represent persistence, endurance, the ability to exist unchanged through vast stretches of time. They're proof that stability is possible even in a changing universe, that some structures can endure essentially forever, at least on timescales relevant to everything we know and care about. And they're proof that the universe has order. Despite the violence of their formation, despite the extreme conditions near their event horizons, despite the breakdown of our physics at their singularities, black holes follow laws. They're described by exact mathematical solutions. Their behavior is predictable, calculable, testable. They're not chaos, they're the opposite. Perfect order expressed in the geometry of curved space-time. As you rest now, under the night sky or beneath your ceiling, know that you're resting under cosmic giants. Above you, if you could see them, are millions of black holes scattered throughout the Milky Way. At the center of our galaxy, 26,000 light-years away, Sagittarius, a star, sits quietly. 4 million solar masses of curved space-time, patient and eternal. In neighboring galaxies, billions more black holes keep their vigil, marking the structure of the universe with their invisible presence. Gravitational waves from black hole mergers that happened billions of years ago are passing through you right now. Ripples in space-time too faint to feel but real nonetheless, carrying information about cosmic events from the deep past. Those waves will continue forever, spreading through the universe at the speed of light, never stopping, never fading completely, just getting diluted as space expands. And somewhere in the universe right now, black holes are merging, their spiral inward counting down billions of years of orbital decay in the final milliseconds before collision. They're creating new gravitational waves that will someday reach Earth, that our descendants might detect, that will add another data point to our growing understanding of these remarkable objects. All of this continues, patient and inevitable, following the mathematics of general relativity and quantum field theory exactly as those equations predict. The universe unfolds according to its laws, and black holes are perfect embodiments of those laws, existing at the edge of physics but never violating it, always conforming to the rules, always predictable in their unpredictability, always stable in their strangeness. Let this cosmic perspective ease you into sleep. You're part of a universe that contains black holes, a universe vast enough to accommodate objects so extreme they mark the boundaries of space-time itself. But you're safe under their distant presence. They're not threats, they're features of the cosmos, markers of structure, anchors of galaxies, witnesses to time. And they're beautiful in their way, beautiful mathematically, in the elegant equations that describe them, beautiful conceptually, in the way they demonstrate the unity of matter, energy, space, and time. Beautiful observationally in the shadows we've now imaged in the gravitational waves we've detected, in the tests of physics they enable. So rest easy, cosmic wanderer. The black holes will keep their vigil. The universe will continue its patient evolution. The mathematics will remain true. And you, in this moment, can simply exist. Breathing, resting, letting go, knowing that you're part of a cosmos that includes these remarkable objects, these serene giants, these patient witnesses to all of space and time. Thank you for joining me on this peaceful journey through the nature of black holes. If you found this exploration calming, if it helped you understand these cosmic wonders in a new light, I'd love if you would like this video and subscribe to Nebula Nights for more relaxing explorations of the universe. Until next time, rest well under the stars, under the galaxies, under the quiet presence of black holes scattered throughout the cosmos. Sleep peacefully, knowing the universe makes sense, knowing that even its most extreme phenomena follow elegant mathematical laws, knowing that black holes, far from being monsters, are actually the most serene, most stable, most perfectly predictable objects in all of existence. Sweet dreams, and may the gentle darkness of black holes ease you into the deepest, most restful sleep.